Hello everybody. Today in this video I'm going to show a problem that was suggested to me on Twitter. And basically you have a closed curve that is graphed by um, this function r equals 3 times the square root of cosine of 2 theta. And it has these weird little intervals which basically make sure that the inside of the square root is never negative. And also um, the the second boundary on theta basically gives you this left part of the curve. So basically this point is the origin, and then PQRS is essentially a rectangle that bounds the entire closed curve. So PQ is a tangent, QR is a tangent, RS is a tangent, and SP is a tangent. And so we're asked to find both the unshaded areas and the shaded areas in this figure. So first off, we can start by finding the total area, or the area of this rectangle, um, which is easily noted by, well, first we can find the length of PQ. And we can see that by symmetry, if I draw this line, that um, this length is half of PQ, and this length corresponds to of r of 0 basically, because what it was denoted by the initial line is essentially when theta equals 0, because theta is the angle that your vector or coordinate makes with the positive x-axis. So if you're on the positive x-axis, then it's just r of 0. And we can plug that into our function here, 3 cosine of 2 theta to the square root, or to the 1/2 power. So 3 times, and then cosine of 0 is just 1. So r of 0 is just 3, which means that PQ is 6. Now we want to find the other length. We want to find QR, and this one's a little bit trickier. So QR is essentially, or we can look at, again, half of QR. So this little leg that we make by dropping perpendicular here. And so we notice that this angle is theta. I'm not even going to attempt trying to write theta there. And this length is r. And so obviously by basic trigonometry that QR over 2 is equal to r times sine of theta. But for a particular theta, we notice that if we were to draw some other line, that basically this vertical length is not as small. And in fact, this vertical length here is the maximum. So we basically have an optimization problem inside of this already complicated area problem. So I'm going to go down here and I'm going to zoom out a little bit so I have not as thick of a writing utensil. So essentially we're trying to find the maximum, hold on, the maximum of r times sine of theta. And I like to point out here that our region, this like small half oval, is from theta is theta basically 0 is less than or equal to theta, and that is less than or equal to pi on 4, because pi over 4 If we plug in pi over 4 to r, we get 0. Um, so we, basically, if we tried drawing a 45-degree line, it would just coincide with the origin. So our theta is going from 0 to pi over 4, and we would like to find the maximum of r times sine of theta. And so we can plug in, essentially we can write this as a function of theta only, so that we have um, a single variable function that we're trying to optimize, then we can just take the derivative. So we can plug in r, which is 3 times the cosine of 2 theta to the 1/2 power, and then times sine theta. So now we have to find the solutions to f prime of theta is equal to 0, because that will give us our maximum. And we're assuming it's a maximum because like you can tell that this is less, and then this is our maximum, and then if we were to draw in another value of theta, I know it's getting crowded, but this is also less. So it's going from small, 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 and then it hits its biggest and then goes small. So we don't have to deal with all the technicalities of like the second derivative and such. I don't know what happened. Uh, my apologies. Okay, back to the problem. So we know we can just take for granted the second derivative test and whatever. We sort of have a geometric understanding that if the derivative is 0, then we have a maximum. Now, so I will take the derivative. It's going to be a bit messy, and um, such is life. So 3 times. So here we just have product rule, and I'm choosing to do that sine of theta first. So that just becomes a cosine theta. And then here, if we take the derivative of this term, we drop down the 1/2. And then, so this is just the power rule. So that becomes a negative 1/2. And then times, we have to take the derivative of the inside, which will become negative 2 sine of 2 theta, and then times sine of theta. So now I'm just going to divide by 3 on both sides. Because we have a 0, we can just cancel out any factors that we see. Similarly, we have a 1/2 and a negative 2 here. So I'm just going to cancel out the 2's and then just say that this is a negative now. And then I'm going to multiply both sides of the equation by the square root of cosine of 2 theta. So the left-hand side will stay a 0, obviously, because anything times 0 will be 0. But here, the square root of cosine 2 theta times the square root of cosine of 2 theta, we basically just have two cosines, and so that becomes just a cosine of 2 theta times cosine of theta minus, and then when we multiply this term, this is the inverse square root, so we're multiplying something by 1 over something, and provided that that something is not 0, we can just say that it cancels out. So we have minus, so the whole purpose was to get rid of this term, and now we have minus sine of 2 theta times sine of theta. And at first, it might be daunting to say, oh gosh, now we have to solve this complicated equation. But this is actually just expanded um, cosine addition formula. This is cosine of 2 theta plus cosine of theta, which is just the cosine of 3 theta. I forgot an S there, but um, okay. So we just have 0 is equal to the cosine of 3 theta, and we know that theta has to be between 0 and pi over 4. Then theta is equal to pi over 6, because we know that cosine of pi over 2 is 0, and so cosine of 3 times pi over 6, 3 times pi over 6 is pi over 2, which gives us 0, and we know that this is definitely less than or equal to pi over 4. So in all, this theta that we were looking for here, that gives us the maximum value, is just pi over 6. And so we can plug that back into f of theta. So we have f of pi over 6, and we will get so sine of pi over 6 is 1/2, cosine of 2 times pi over 6 is cosine of 1/3, cosine of pi over third, which gives also 1/2, but it's under the square root. So 3/2 times the square root of 1/2. After simplifying, we just get 3 times the square root of 2 all over 4. And so that is equal to, as we saw here, that is equal to QR over 2. QR over 2. So not only do we now know PQ, we now know that QR is equal to 3 times the square root of 2 over 2. Great. Now we know that the area of PQRS, that rectangle, is equal to PQ times QR, which is equal to 9 times the square root of 2. And if we read the question again, we're trying to find the area enclosed by the curve, which is unshaded, and the area bounded by the curve and the 4 tangents. So basically these two areas have to add up to 9 square root of 2. So obviously the easiest thing to compute would be the area bounded by C, this unshaded area, because that's just an integral. Now, we notice that by drawing more lines of symmetry, the curve has 4 equal pieces, like this piece that we were fooling around with earlier. And like we saw that this is from 0 to pi over 4. So the total area is just 4 times the area in that piece. So from 0 to pi over 4 are our integration limits. Now we should remind ourselves, how do we find the area in inside of a polar function? Because it's different than integrating a normal function. So off to the side here, I'm going to show that essentially if we have our origin and think about in normal integration, right? We split everything into little rectangles because we can find the area of these rectangles. Basically, think of Cartesian coordinates as rectangular coordinates and think of polar coordinates as circular coordinates. Then, if we have some little d theta, we're trying to calculate the area of this little wedge, which for very small d theta is just a circular arc with radius r. And, and so the sector formula gives that this is 1/2 r squared d theta. That's the area of a small circular arc with angle d theta and radius r. So obviously r has to be a function of theta for this integration to work. And of course we do have that r is a function of theta. So now we just have to plug in, so we have 1/2 r squared is, finally we get rid of that square root, and so we get 1/2 and then 9, then times the cosine of 2 theta d theta. This is the integral we now have to evaluate. And if we look at the substitution u equals 2 theta, then we will get, we can rewrite this entire integral as 9 times the integral from 0 to pi over 2 of cosine u du. And I'm not going to go through all the steps of this, but you can check yourself that this is just equal to 9. And so this is the answer to part A. This is the area bounded by C. This is the unshaded area. Great. Well, now the answer to B is just this rectangle minus the bounded area. So it's just 9 root 2 minus 9. And that is the answer to part B. Thank you for watching, and I'll see you in the next video.